Okay, so let me share my screen. Right, so what I'm going to do to start off with today is I'm going to do a little bit of statistics. It's for biology, so I will pop that bit of information in now because obviously you don't need it for chemistry, but you do need this information for biology. So what you can see here, it says Edexcel. Don't worry, it's just that Edexcel have a really good booklet with all the stats in, so I can show you some good examples. But the statistics are exactly the same no matter what exam board it is. So the AQA stuff is exactly the same as OCR, same as Edexcel, so don't worry. But basically they made a really good maths book with some really good examples in it for us to use. So let me just find where I want to go to. I want to do statistics. I want to do on Petty test. I'm going to go to page 40. Okay, so basically, statistics come in stuff a lot. I'm just sort of going to talk through a few bits, have the information up, and sort of talk this through with you, and then look into specific tests. So there's a few basic maths skills that you have to be able to do, which I know your maths is really, really good and really strong. So I'm not going to sort of go through and teach you how to find the mean, for example. I'm not going to talk you through finding the median and the mode. I know you're perfectly capable of doing those, but I will just sort of let you know that these are things that they expect you to be able to know how to do for the statistics part. So we'll cover some of the other maths stuff as well. And when I say cover it, I'll probably just sort of go through and go, this is the sort of maths that you're expected to be able to do at A level and can come up in the exams. So in biology, there's statistics, and statistics, we use them basically to see if when we've done an experiment, there's actually some genuine significant difference in our results, because actually there is no point doing a test, getting some results, and then us sort of looking at it and going, well, actually, I have zero clue what these results mean. Is there actually a difference? Is there not a difference? So rather than back at GCSE where we go, oh yeah, there seems to be quite a big difference between them, we bring in statistics down there, a mathematical way of saying what is the probability that our results are actually different, or is actually could they be different just due to chance? So we're looking at that. So it's sort of a probability type skill. Now, summary of statistics, you'll regularly get asked to look at the central value of the sample. So as you know, that could be classed as the mean, median, or mode, which all three are quite different. They're really useful because obviously when you're doing an investigation at any point, you want lots of replicates. When we're doing these replicates in the exam, if you get any sort of question where it's asking you to design an investigation, tell us how you might plan, let's say, an investigation to see which nutrients are best for a plant to grow in, for example. You're going to want to have replicates. Whenever you're getting asked to talk about anything in these exams, you want to mention replicates. You're going to want a large amount of replicates, a sensible amount of replicates, a large GCSE, we'd always say 3 or more. I would say at least go with 10 or more. But yeah, something along the lines of a good amount of replicates. But because we're doing replicates, obviously we want a central value. We want the average of those replicates. So we might want to find them by using the mean, the median, or the mode, which I know is really quite basic and simple. So I'm not going to go through how to do every one, but obviously we've got an example here. This is a sample showing a resting heart rate in beats per minute of 16 men, and then you could be asked to find the mean. Obviously what you would do is you would add all those values together. Here is the official mathematical formula of a mean. So add all those values together and then divide it by how many there is. So for these 16 men, the average, well, the mean beats per minute would be 73.25 beats per minute. I was quite naughty to use the word average there. Don't call the mean the average at A level, because technically average can apply to both mean, median and mode. It's a bit vague. So when calculating a central value, be clear if you're using the mean, median or mode. As per usual, most people choose the mean. It's the best choice if your data is normally distributed. And normal distribution is where we've got no outliers, no anomalies, and it's not heavily based at one end or another. So I'll show you some differences between normal and skewed distribution. But a normal distribution would be, you've got basically, if we drew it as a graph, all these values, it would sort of look like this. We've got less here, and then we get that sort of peak and rise. So the lower values, we've got less of, clusters in the middle, and then drops again. So that's a normal distribution. We would call this a bell-shaped curve. That's a normal distribution. And so, yeah, that's how you can calculate the mean. You regularly will need to calculate the mean. You often won't be asked to specifically calculate the mean. You may get given a set of data and asked to analyze it. And in that situation, yeah, mean would be great for you to use for that situation. We do obviously have the median and the mode as well. Median, as you know, is that middle value of a sample. It's again, we only really want to use median if our data is not normally distributed. So something like ranked data. So smallest to largest. So for example, trying to think of something for ranked data. If we're looking at, I think something that might have a ranked data in, looking at smallest to largest, yeah. You then want to try and find that middle value. So yeah, anything you can rank, maybe who comes first, second, third, that sort of thing. So yeah, you are just literally finding that middle replicate for the median. And obviously if it's an odd number, you find the difference between the two. That will give you your median there. So that's the median. Only going to use it if the data is not normally distributed. So non-normal distribution, if we had it on a graph, might look like this. It might look like this. There's our graph part. It's not going to be a bell-shaped curve. Mode, obviously, is the most common or frequent replicate value. This is really, really useful when there's a very, very, very large number of replicates. So we're talking hundreds, possibly thousands. When people use a mode, there's often a frequency table or a plot or histogram involved to look at the distribution of the replicates. So in those situations, sometimes a mean isn't suitable. So we might use the mode instead. We can apply the mode to quantitative data, in which case we call it the modal value, but we can also use it for qualitative data as well. And in that situation, we'll call it modal class. And we can have more than one mode. So that's if more than one value is equally frequent. So for example, in this data set, 74 is the modal value. But if you had the same number of 74 and 75, for example, you would have 74 and 75 both as your modal value. So if you've got a large number of replicates, then it's really, really helpful for you to draw it in a frequency table instead. And you can find it that way. And like this, we can also use it for categoric data. So if you were going out with a quadrat and surveying a plot of land, and we want to say, well, which type of plant was most abundant on a field, a tally chart, frequency table, then to find the modal category. And in this case, it'll be Buttercup. So you can use that there. So, but in this situation, it'll be a modal class because this is categoric data. Always, always, always look for any outliers, anomalies from a set of or replicates before calculating any type of mean. But only do this again if the anomaly is very different from all the other results. So we say generally by rule of thumb, factor of 5. But if you're calculating median or mode, we don't remove anomalies because those values aren't affected by anomalies. So we only remove anomalies if we're dealing with mean, and that's only if they're different by a factor of 5. That was just a quick overview. Dispersion of a sample. This is actually quite important. Again, I know you'll know how to calculate range, but dispersion of sample does come up a lot. Again, when we're talking about things like species richness, species abundance. Range, as you know, is just a difference between your maximum and minimum values. Nice and simple. Standard deviation does get used quite a lot. I'm just going to give you sort of a quick rundown of what standard deviation is. Basically, standard deviation uses 2 bits of information. It needs the mean. So if you were to work out standard deviation by yourself by hand, lots of computer programs, just things like Excel can do it for us, but if you're going to work it out yourself, you would need to know the mean for your data already. And all that standard deviation is, it's that dispersion of your data around the mean. So basically, what is that deviation from the mean? How much lower and how much higher does the data go, basically? So we can calculate standard deviation from all that replicate data that you've got. And we use that mean as that, or where around it. So it's more representative than the range. The range just basically tells us, well, what's the difference between the highest and the lowest? Not that great because we're not looking at all of the different bits of data. So when we're involved in the mean, then we're looking at, okay, well, what's the difference between the mean and the lowest value? What's the difference between the mean and the highest value? So the larger your standard deviation, the larger the spread of data. And we would often say that then that would be less reliable. The smaller the spread, the more reliable. So for example, 68% of the sample replicates will be found in the range mean. And then 95% of sample replicates will be found in the range mean plus 1.96. So whenever a mean is calculated, standard deviation should also be calculated to indicate the quality of the sample of the mean. So that's something really important to remember. So whenever you're going to calculate the mean, you should always be calculating the standard deviation as well. And that is to indicate the quality of the sample of the mean, because your mean might be rubbish. And I'm not meaning like what you're actually calculating is rubbish. It could literally be that your data set is rubbish that you've been given. So actually we're looking at that quality. And so we can write that summary as this. So for example, mean height would equal 1.62 plus minus 0.08 meters. And that plus minus 0.08 meters is your standard deviation. So it can be plus or minus 0.08 meters above or below that mean. So then the higher this part of the value is, that shows the larger the spread. So how we can calculate standard deviation is using this formula here. So standard deviation is calculated using this formula. And what it does is it shows it's calculated by summing our squared differences between each value. So these are our differences between each value and the mean. So we sum up the differences between each value. So that's our values. That's our mean. Square it. And obviously the bigger the differences, the bigger the standard deviation. And then that n is obviously the number of data sets we've got. You can show it in a different way. Let me see. We've got it on there. I'm also going to go through chi-squared with you as well. So yeah, so lots of people use this one as well. So this part just being your sum of, again, sum of ex squared 2. And then this is obviously your each measurement. So this was if you're working out standard deviation for each measurement. That's the n is then your total number of measurements. So this would be your sum of. Then this is going to be for each measurement. And then that one is going to be total number of measurements. So this shows another version of the formula. It can look more complicated, it can be easy to use because you don't actually have to calculate the mean first. In this one, because we've got this part, you need to calculate the mean first. This one you don't. However, the easiest way of calculating the mean and standard deviation, is to use the statistical function of a scientific calculator. You can get a scientific calculator to do all this for you if you input a table. So really quick example, I'm going to go through here. So we've got a table here, and we're talking about lengths of a snail shell. So we've got 12 snail shells and their shell length. You're asked to calculate the mean and the standard deviation for this sample. So there's two ways we can obviously do this. So to calculate the mean, obviously you just add up all the lengths, which totals 523, and then obviously divide it by the total number of data sets, which is 12. So you do 523 divided by 12 and give us a mean of 43.6. So our mean, I'm just going to write our mean up here. So we've got 43.6. Then we need a standard deviation for the mean. Now this column is then where we're going to work out standard deviation for each different one. So what you would then do is that first row, we do x, which is 32, minus the mean, which would be 43.6 squared, which gives 134.6, and you do that the whole way down, and then you total it at the bottom. And that gives us our total there. And then we'll fill in the values for the standard deviation formula. So then at this point, part left of our standard deviation, because we've done the complicated part, it would be 1124.9, and then it would be n minus 1, n minus 1 obviously being 12 minus 1, which is 11, which would give us 102.3 square root that, which would give us 10.1. So our standard deviation would be 10.1. That would be 4.36 plus minus 10.1. Error bars, I'm just going to talk through what they show. Basically, the cross on the error bar is your calculated mean, and then the top and the bottom of these are your standard deviations, your top standard deviation and your bottom standard deviation. It just gives us that visual representation of that spread of data, and it just really emphasizes the point that a calculated mean value isn't perfect and it's not the true value. We do have this standard deviation on either side. In an exam, whenever you're given error values, either as a number in a table or as error bars in a chart, you should look for overlap. And this is really, really important. So, you know, when you're given lots of questions where it's like, discuss the results, or you might get, for example, when we were doing those ones about cancer, when we were looking at the different treatments on the mice, and that is where you want to look for overlap. So either in a table or as error bars on a bar chart or a graph, you are looking for overlap of standard deviations. If error bars overlap, then you can conclude, and this is really, really important, if error bars overlap, then you can conclude there is no significant difference between the mean values. So that's really, really important. So without doing a statistical test, which we'll go through in a minute, without doing any of that, you can say that because the error bars are overlapping, there's no significant difference between those mean values. Whilst those mean values might be different, the rest of the data is overlapping. Conversely, you can also say, well, if my error bars don't overlap, you can conclude that the mean values are significantly different. We're going to look at a better way to test the significant differences, but if that's what you're given, you're not asked to do anything else, that is something you can say. So here's an example. So the effectiveness of 2 antibiotics, penicillin and tetracycline, on the growth of 2 species of bacteria was investigated using a disk diffusion assay. There were 24 replicates, n equals 24, and the bar chart shows mean diameters of the inhibition zones around each antibiotic disk. The error bar shows plus minus 1 standard deviation. What conclusions can be drawn from these results? So when we look at these, if you drew them across, what you would be able to see between the E. coli being treated by tetracycline and the S. albus being treated by tetracycline, you can sort of see there's actually not much difference between them. But really, you're going to want to compare them this way around. So E. coli being treated with penicillin and the E. coli being treated with tetracycline. Well, we've actually got 2 very different means. The error bars don't overlap at all. You could conclude from that there's the mean values are significantly different. And you could also say that about the S. albus and penicillin and the S. albus and tetracycline, they don't overlap. So let's have a look. So the error bars for the 2 penicillin results don't overlap. So penicillin is significantly more effective against S. albus than against E. coli. Because we want our inhibition zones to be larger, yeah, so we can say that it's more effective on this one than this one. The error bars for the 2 tetracycline results do overlap, like we said here. These ones do overlap here. I mean, that's me drawing it badly. So there's no significant difference in the effect of tetracycline on either of them. It's as effective on both of those illnesses. The error bars for tetracycline don't overlap with those for penicillin, like we said earlier. The tetracycline is significantly more effective than penicillin against both species of bacteria. So you've got those 3 different points just from looking at those error bars. That's really important to look at. So statistical tests. I'm going to draw something out for you in a second as well. Stats are, I quite like stats, they're quite good. Basically, you'd be asked to carry out statistical tests. The point of them is to tell us if something that we see in an observed effect is real or if it's just due to chance. So for example, these results, are what we're seeing here real or is it just due to chance? And it's going to be more reliable than just saying, do the error bars overlap? Yes or no. So for example, here they're using the example of, we find that mean light intensity is lower in deciduous wood than in coniferous wood. Is this difference real, or did we by chance choose darker sites in the deciduous wood? The first thing we have to do is we have to come out with something called a null hypothesis. So you're probably really, really used to hearing of giving hypotheses all the time. Hypothesis is, I hypothesize that if it's if I give my plant water and sunlight, it's going to grow better than a plant that I don't give water and sunlight to. The null hypothesis is what a statistical test is based on. And it's a mathematical model. And it basically states that there is no effect. So when you are asked to write a null hypothesis, you're looking for no effect. So there is no difference between groups, or there's no correlation between variables. So the null hypothesis is fixed for a given test. And we must state the null hypothesis when we've chosen our test, so we're clear about what exactly we're testing for. So for example, this one at the top, so suppose we find that mean light intensity is lower in a deciduous wood than in coniferous wood. My null hypothesis for this could be something along the lines of there is no difference in light intensity between the two types of wood. And that would be our null hypothesis. You'd obviously use deciduous and coniferous, but I'm not writing all that out at the moment, but you get the idea. There is no significant difference. That is what your null hypothesis is. It has nothing to do with and can be really, really different from the scientific hypothesis you're actually making about results of the experiment. Alternate hypotheses are the opposite of a null hypothesis, but the alternate hypothesis isn't needed for a conclusion. So we just don't bother with it. Really important, the word significant cannot be used in the null hypothesis as it has no meaning here. Okay, so we just say there's no difference or there's no correlation. We don't need to use that word significant. Later, when we look at p-values, the word significant is important. So at the moment, when you make your null hypothesis, you're just saying there is no difference between. There is no correlation, and that's literally it for your hypothesis. Yes, there is. No, there isn't, and that's it. So before we look at actual specific statistical tests, I'm just going to talk to you something about a p-value, and p-values are going to come up loads. When you do any type of statistical test, it could be an unpaired t-test, a student t-test, Spearman's rank, chi-squared. I'm trying to think of some others off the top of my head, but I can't. So when you're doing any sort of statistical test, it returns a probability. So a statistical test is just a mathematical model for probability. And we call this the p-value. It's our probability value, and it has a scale of 0 to 1. Okay, so nothing on it. If you ever get a p-value higher than 1 or lower than 0, you've done something wrong. So you need to redo your test. All this p-value is, it's the probability that our results would be obtained if the null hypothesis were true. Now, this is where sometimes people's heads go, hang on a minute, I'm really struggling to understand what's happening. So the p-value is the probability that our results would be obtained if the null hypothesis were true. And so any observed effect that you see is just due to random chance. So if we go back to that tree idea, we're then saying that the p-value is the probability that results were obtained just by chance. So actually that light intensity, the difference between those two types of wood, there's no real difference in light intensity, it's just random chance. So we're hoping for a low p-value. The lower your p-value, a low p-value means that the effect in the results is probably not due to chance. So we say the effect, I'm going to change the colour for this because this word's really important. We say the effect is significant. So if you have a p-value, and we usually use 0.05, which is 5% or 1 in 20 as a cutoff. If your p-value is lower than 0.05, we say that actually those differences between those two values, or 3 values, 4 values, whatever we're comparing, but let's say 2 values, the difference between those 2 values we're comparing is not due to chance, and in fact they're statistically significantly different. There is a significant difference in them, not due to chance. There is an actual definite difference there. And this cutoff is called the significance level of the t-test, of the test, sorry, not the t-test, of the test. So that's our p-value. When we have a cutoff point, we usually use 0.05, which is 5% or 1 in 20. So you have two possible conclusions when you do a statistical test. You're either going to have a p-value that is greater than 0.5, and this means that the probability is greater than 0.05 that the observed effect is due to chance. We then reject the null hypothesis and conclude sorry, I've just read my greater than and less than symbols the wrong way around. So if our p-value is less than 0.05, this means that the probability is less than 0.05 that our observed effect is due to chance, which would mean we reject the null hypothesis and conclude that there is a significant effect. Conversely, if our p-value is greater than 0.05, this means that our probability is greater than 0.05, well, 0.05 or greater. And so our observed effect is due to chance. So we accept the null hypothesis and conclude there is no significant effect. It's really important you learn all these parts of these alternative conclusions and you use them when you have to write a conclusion in an exam. They're really important. They could get you lots and lots of marks. So knowing that p-value and knowing what it means if it's above or below 0.05. So I'm just going to sort of give you a different lowdown of sort of writing out p-values. P-values are what sort of usually are what throw people the most. I'm just going to do a new screen share. Let's just move all this. Here we go. Right. So let's zoom in on this a bit. Right, here we go. So our p-value is 0.05. Let's do this as our cutoff point down the middle. So if we have a number smaller than 0.05, we might have a number bigger than 0.05. This is our critical value. 0.05 is our critical value. So we call this C, critical value. So if our p-value is, so if our p-value equals, no, I don't want to equal, is smaller than our critical value. So if whatever we've worked out, so it could be our results of our t-test, whatever, if it is smaller than 0.05, it means that therefore we have 95% confidence there is significant difference so we have confidence there is significant difference or correlation exists. I'm struggling to spell. In that situation, we accept our we accept our normal hypothesis, and we would reject the null. If it's bigger, then we say we have less than 95% confidence. We have less than 95% confidence that there is a significant difference between the samples or that correlation exists. So then we would reject the hypothesis and accept null. So that's the rough idea of what we do with p-values. So let me screen share again and take it back to where we were, biology maths. Here we go. So yeah, I was using critical values there. That's because we can't calculate the p-value ourselves. So effect is significant, then we report the effect size. Basically, we can't calculate p-values ourselves. We calculate a test statistic, and then we compare with a critical value to determine whether p-value is greater or less than 0.05. So in this situation, you're given a set of critical value tables, and these will be provided in any exam that needs them. Okay. So down here, I'll show you some examples of critical value tables for t-tests, chi-squared, and Spearman's rank. So these are all shorthand for those three tests. So that's t-test, chi-squared, and Spearman's rank. In the exam, the table may look a bit different, but they have the same features. Whenever you're going to use these tables, you need two pieces of information. So when I was talking about critical value here, that's when basically your t-test, whatever your test result is, so if it's t or Spearman's rank or whatever, less than that 0.05 critical value, so it's less than that critical, or here that would be greater than the critical value, whichever one it is. So here t is going to be smaller than our critical, and here our t is going to be greater than our critical. So screen sharing, get back to where I want to be. Share. So two things you need when you're doing this is you need your significance level, and that is the level of significance or certainty we want in our conclusions. We usually use 0.5 in biology, 0.05. You can choose other significant levels. They'll be found in the tables, but we generally use 0.05 in biology. And you'll also need your degrees of freedom or number of pairs for Spearman rank. Degrees of freedom is generally one less than the number of results you have, so n-1 basically. But you have to learn the exact degrees of freedom formula for each test. So we'll talk about one of them today, and then tomorrow we'll talk about a couple of others as well. So basically all you would need to do is find the column for your significance levels, so normally 0.05. So if you've done a t-test, you find the column for 0.05, which is here, and your degrees of freedom. So if you were using a number of results, so if you were doing one that got degrees of freedom of 1, your significance value would be 12.71. So you can see there. So for example, for a t-test with significance level of 0.05 and degrees of freedom of 7, our critical value would be 2.36. What you then do is you compare this critical value with your calculated value to find the p-value for this test. So if the critical value, which is 2.36, is greater than the calculated value, then your p-value is greater than 0.05, which is what I have put here. Let me show you here. If your t-value is greater than your critical value, then your p-value is greater than 0.05, which means p is greater than 0.05. If your t-value is less than your critical value, that will mean your p-value is less than 0.05. And that's roughly how it works. Let's go back. And you do the same thing. So if you're doing chi-squared or Spearman's rank, but you'll be given these tables if you need them. So this is where we're just going to start talking about the correct types of tests that you need. Realistically, there's loads, but for A-level, you only need to know about 4 types of tests. There's the t-test. You will sometimes in some books see it being called the student's t-test, but the t-test. There's the pair t-test, Spearman's rank correlation, coefficient, I always forget to include that bit, and chi-squared. So we'll start looking at t-tests today. And then, yeah, that t-test, also called student's t-test, also sometimes called the unpaired t-test. You'll probably hear me calling it the unpaired t-test. It's what I'm used to calling it. So if you're given a set of data in an exam and you're asked, okay, do some statistical analysis on this, you need to know which of those 4 you need to do. You know it's going to be one of those 4, but you need to know which of the 4. So first you need to decide what you need to do with it. And basically there's 2 kinds of experiments, and they're characterized by different types of charts. So are we comparing data? Is our test comparing data? Is the experiment we've done a comparison of data? Or is it correlation of data? Depending on if we're looking for correlations or comparisons, will depend on the type of test we do. We also need to know what kind of data we've been collecting. So 2 types, as you'll know, there's quantitative, which is numeric data, or qualitative, which is categoric. Categoric data is pretty rare, and it mostly occurs in genetic crosses. So let's have a quick look at what we would choose to do then. You can use this table to choose the best. You'll often be able to work it out a lot yourself. So do you want to just summarize the data? If you just want to summarize data, you can actually get away, if it's numeric data, quantitative data, just doing the mean and your standard deviation. If it's qualitative, something like genetic crosses, you just need to tally your frequencies. If you're going to compare 2 sets of data, so it would be something that would be presented in a bar chart, you're going to either do the unpaired t-test, like I was saying before, a t-test, student t-test, unpaired t-test, which is when you've got independent samples, or you're going to do the paired t-test for when you've got matched samples. We'll talk about those differences in a bit. If it's qualitative, chi-squared, genetic crosses, that's the only time really you're going to use chi-squared. If it is not a genetic cross question, you can straight away go, I don't need to do chi-squared, which then leaves you with Spearman rank correlation, unpaired t-test, t-test. If you're not looking for correlations, you can get rid of Spearman's rank. So then all you need to do is decide between unpaired t-test or paired t-test. So yeah, if you're correlating 2 sets of data, Spearman correlation. We don't need to do qualitative as that. So here's an example. You want to know if grazing affects the abundance of certain grassland plants, and you're going to compare 2 areas, a grazed field and an ungrazed field. And you would use quadrats to collect numeric abundance data. So that's really important, numeric abundance data. You could then plot a bar chart with 2 bars. So the correct test in this is the unpaired t-test. And I'll talk about why now. So here's some clues. It's numeric straight away. That lets us know it's going to be a quantitative set of data, which means straight away we know we're not going to be doing chi-squared. We're going to be comparing 2 areas. We're comparing 2 sets of data. We know it's not going to be Spearman's rank. 2 different areas. One's a grace field, one's an ungraced field. That means they're not matched samples. They're unmatched samples. They're independent samples. They're separate from each other, which means we're going to be doing an unpaired t-test. If you're not sure what test to do, sketch down what graph would I use. If you've got a set of data, or this sort of data I'd get, what graph would I use? Would I use a scatter graph? Would I use a bar chart? Bar chart, right. It's going to be a t-test of some form, or chi-squared, or is it going to be Spearman's rank? Like I said earlier, whatever experiment you do, all statistical tests work better with a large sample size. The examples and exams in the guide often have sample sizes of 10 or less just for convenience, and that's really important. But for real investigation, plan for at least 30 and preferably 100 repeats. 3 repeats may be acceptable for school lesson, but it's quite unacceptable for a serious investigation. So if you're planning an experiment in an exam, go with at least 30, maybe just say 100. But in the exam, you're always going to be given data of 10 or less, just because otherwise you'll be spending a huge amount of time just working out means, for example. So I'm going to introduce you to the unpaired t-test. Quick talk about it, and I'll give you the formula for it, and then we'll have a look at it in a bit more detail tomorrow. So unpaired t-test, also known as the t-test, also known as student's t-test, tests for differences between 2 sets of independent data. The unpaired t-test tests a null hypothesis that, and this is important, there is no null hypothesis, that there is no difference between the means of the 2 sets. I'm going to write out the t-test on the other page, and we're just going to talk through the formula for it. So right. T-test, here is your formula. Handwriting's got a bit strange. Oh, here we go. I've deleted too much, right? So oops. Okay, let's have a quick talk through this. So what does all of this mean? So this is the mean of the first sample. So remember, paired t-test, we're comparing 2 sets of data. So we're not going to have loads. So you can guess that's the mean of the first sample. Probably guess that. That's our mean of our second sample. So you're going to take away the mean of the first sample from the mean of second sample. S1 here is your standard deviation of your first sample. S2 is going to be your standard deviation of your second sample. N1, number of measurements in first sample. So number in first sample. And as you can guess, that's number in second sample. Let me see if we've got. So a couple of rules about the t-test, well, unpaired t-test. I'm just going to pop it over here so we can see it. It's a statistically significant difference between two sets of data. We can use it in a sample less than 25. If we've got more than 25 data sets, it gets too complicated. So it needs to be in a sample size less than 25. And the data needs to be normally distributed. So a quick look, let me share screen now. Right, so a farmer compared the effects of two different fertilizers on the yield of potatoes. He grew potato plants in many pots and treats each plot with equal masses of the two fertilizers, A or B. After a set time, he dug up the potatoes and recorded the yield for each plot with the results shown in the table below. One of the plots was damaged by animals and yielded no potatoes. Which fertilizer is best? So obviously, to do the t-test, we need means of sample 1, means of sample 2. So obviously, you're going to go through and work out the mean of sample 1. Mean of sample 1, we're going to add all of those values together, divide by how many there is, and there was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So add all those together, divide it by 10, that would give us 20.20. So our t-test by this point would be looking something like this if we popped it in. So we'd have 20.20, and we're going to take away the mean for the second one, which would be 23.44. Have that over this. So we need standard deviation of our first sample. So our standard deviation of first sample is 3.22. That's going to be 3.22 squared over the number of samples, which is going to be 10. And then we add that, and standard deviation for our other side is 4.10. Some samples 9. That is how we'd work out our t-test. Put that through in our calculator, and this is what we would get. So we choose a t-test. We would need to state our null hypothesis. So there's no difference in mean yield between the two fertilizers. Calculate the mean of each set, like I said. Calculate the standard deviation of each set. Count the number of measurements in each set. And then put all the values into the formula to calculate unpaired t-test. So like I was just showing there. So I think I might have forgot to square. I squared that one, I forgot to square that one. So this is what we would end up with. We'd end up with this value, 1.89. So our t-test gives us a value of 1.89. Before we do anything else, we need to calculate our degrees of freedom, because obviously when we look at that critical value table, we need to know what our p-value is going to be and then compare it to our degrees of freedom. So our degrees of freedom, doesn't matter that our samples aren't the same size, we just add them up for the two. So degrees of freedom for sample 1, which is 10 minus 1, which would be 9, and then for sample 2 would be 9 minus 1, which is 8. Add them together gives us 17. So our degrees of freedom is 17. So using a table, we'd look up a critical value of t for a equals 0.05 and degrees of freedom, which is 17. So if I can find one of them, let's go back up. What was our degrees of freedom? 17. Our value is 1.89. Here we go. Right. Degrees of freedom was 17. 1.89. So our value is less than our critical value. So this value, our t value, is less than our critical value. So compare this value of t, which was 2.11, with our calculated value, sorry, critical value of t was 2.11, our calculated value is 1.89. So our critical value is greater than our calculated value. So our p-value is greater than 0.05. Okay, so our critical value is greater than our calculated value. So our p-value, therefore, is greater than 0.05. So the probability is greater than 0.05 that the observed difference in the means is just due to chance. So we accept the null hypothesis. There is no significant difference between the two fertilizers. So what I will do is I'll leave that there today, and I'll get some other examples and we'll talk through them tomorrow. So we'll look at the other type of t-test, chi-squared and Spearman's rank, and we'll go through a couple of exam questions and talk them through and write some answers. So I will see you at 1:30.